I'm in touch with Mike. We're working together.
Last session of the winter school, a bit late starting because we've just been working on the certificates. We wanted to wait till the end of the final lab session to make sure we weren't going to fail anyone. So well, I think the plan is they're going to be pretty signed. So we'll do that before the brewery visit, which is tonight. And stamped. We've even got stamped. Very professional. That's all the important stuff. So it gives me great pleasure to introduce Rich. I first met Rich when actually at the same meeting where I met Hans Wackenagel, who's here and speaking tomorrow, which was on a meeting on multi-output Gaussian processes, at which time he was working on Gaussian process emulation with Tony O'Hagan and Jeremy Oakley. He's a lecturer at statistics now in Nottingham. He's actually most well known for an approach called ABC, which is Approximate Bayesian Computation, which is a really interesting approach that Rich worked on in his thesis with his supervisor, Simon Tabaret, for doing Bayesian inference in very complex simulation systems. But he's also interested in Gaussian processes and using Gaussian processes to assist that sort of thing, and so he's a great person to give us a sort of statistical perspective on Gaussian processes from maybe someone who hasn't fully drunk the Kool-Aid, but someone who thinks they might be interesting models for using for various different things. So over to you, Rich.
Thank you. So I've been asking Neil since about November what he'd like me to talk about, and he's yet to give me an answer. So I thought what I'd do, what I thought before this week I was going to do, was just talk about 2 or 3 different application areas where Gaussian processes are useful. And I'll still do that a little. But there's a couple of topics that arose during the week that I thought no one had really commented on, and they're just kind of mentioned in passing, particularly sampling of hyperparameters. So I thought I'd add in a few slides yesterday on sampling and the benefits and how we can do it and how well it works and so on, particularly in sequential settings. So I talked a bit about hodgepodge, so if you want to interrupt me, you can do at any point, it's fine. Okay. So just to set the scene, just to kind of follow on from what Jeremy talked about yesterday, the kind of problems I'm interested in I'm interested in working with scientists who have simulators, and particularly simulators where they've built in physics to them. They've got some kind of scientific knowledge, they've encoded this in a computer program, and they run this program to try and make predictions about the world. Okay? So the most important and most famous kind of case where computer simulators are important is climate science. So your basic climate simulator has the sun with energy coming in, you've got oceans and they circulate, the oceans drive the climate. Then as you get more complicated, you have an atmosphere, and perhaps the atmosphere circulates as well. And you have heat transfer between the atmosphere and the ocean and the sun. And then perhaps you had more things in like glaciers, clouds, wind, precipitation, the plants, and so on. Okay. So you get these very complex computer models, and we make predictions with these. Okay. And these predictions matter, right? We are potentially talking about reorganising the world's economy on the basis of the predictions of these models. Yeah? That's where most of our knowledge comes from, what's going to happen in the climate in the future. So what's the problem with what we're doing with these things? Well, you've probably seen this figure before. It's an old figure now. It's from the last IPCC report 6 or 7 years ago. There's a new IPCC report out last year, but this is, I haven't updated my figure. So what this picture shows is the prediction about what future climate is going to be, a global average temperature, over the next 100 years, and it's made by 8 different models. Now, they're essentially only a very small number of climate simulators, because each one of these, the Hadley Centre model is over 1 million lines of code. Yep. These are all in big governmental research centres, by and large. They're not universities mostly running these things, because they are big professional efforts that require a lot of funding. So what we've got here are 8 different models and 8 different predictions with increase of temperature from about 2 degrees to about 5 degrees. So what do we think climate is going to do? Yeah. We've got a range of predictions. Do we just take something along the middle? So we say it's going to be 3 degrees. What? Well, if we went to the Hadley Centre, so it's the UK's one in Exeter, Met Office, and asked them what they thought. They don't really think the temperature is exactly going to do this. This is just one run from their model. Okay? They're just, these models, a million lines of code, there's lots of knobs and dials and parameter settings we have to tune, and this is just what one of those settings gives us. So really, if they're able to, what they'd like to have is a cloud, kind of a region, a band of uncertainty showing the range of possible outcomes. Well, they don't really know how to do this at the moment because these simulators take between about 1 or 3 months to run on a supercomputer. They're massive, complex things. So we've got this unfortunate situation where all the models have the same physics, and they all know the same thing. We've got this range of predictions, but each model's not, each simulator's just given a single prediction, and we want to be able to say something about reality. So these are the kind of the questions I'm interested in. Given a simulator, how do we make inferences about the real world from this simulator? And you can break this question down a bit. So Jeremy mentioned all these things yesterday, but one question is, how do we relate simulators to reality? Yep. Experimenting on a simulator isn't the same thing as saying what the reality is going to do, the real system. So you have to somehow say how the simulator relates to reality, because we know simulators are wrong, so how wrong? Okay. Another one is, how do we estimate these tunable parameters, calibration? Well, you know, there's lots of these settings, levers, knobs and dials. How do we get the right setting? One is, how do we deal with computational constraints? If your simulator takes 3 weeks or 3 months to run, you can only afford to run it a small number of times. But even if it takes a second to run, you're still limited in how much you can learn. If you've got a 1,000-dimensional parameter space, a second is a long time for your simulator to run. You can't explore very well. And how do we make uncertainty statements and so on? So, from my point of view, all of these questions are tackled by methodology that uses Gaussian processes in some way or another. I mean, there are obviously different ways of approaching them, but in some ways, the Gaussian process methodology has made key kind of contributions to all these areas. So I'm going to talk today about the top 3 a little bit and just touch on each of them. Okay, so that's kind of just setting the scene a little bit. We'll come back to an example in a minute, but what I thought I'd first do is a little bit of technical material that people have talked about, but no one's really shown whether it's a useful thing to do or not. So this is sampling of hyperparameters. So what we've had all week is we've got some model, some unknown function f, and we've modelled it by a Gaussian process with a zero mean and a covariance function. And that covariance function is dependent upon other parameters, which I'm going to call psi. So, for example, I think the most common covariance function we've seen is the exponentiated quadratic. Yep. So we've got 2 parameters in this. We've got a variance parameter that tells us how variable our function is, and a length scale parameter, which I'm going to call lambda, which tells us how quickly it varies as you change the x value. Then we might have noisy observations of this function, so y given f, perhaps there's Gaussian error, so we've got another parameter, tau squared, which is kind of the observation variance, or in statistics you might call this a nugget term. Okay, so we've got these 3 parameters. How do we learn them? Remember, how do we estimate them? What are we going to do? So I think the approach that everyone's taken so far is a kind of a plug-in approach. So we use some method, whatever it is, to estimate them, estimate a value, fix that value, and then use that value for all our predictions. So for example, we might decide we're going to use the maximum likelihood or the map estimate. So this is the map estimate here. We've got the probability of seeing the data given our covariance and the parameter times by the prior parameter, and we just find the value of the parameter that maximizes the posterior, essentially. Okay, so this is our map estimate. And so all we do when we want to predict the value of y star at some new input x star is we just take our estimate, psi hat, and plug it in. Okay? So that's the kind of the plug-in approach. But we might decide we want to be a proper Bayesian, a good Bayesian here, okay? And integrate out the uncertainty in psi. If we do this, we're ignoring the fact that we've estimated psi. There's a range of values of psi that are feasible, and we might want to take into account that uncertainty. Okay? But it's going to make our predictions more uncertain, but perhaps that's not uncertainty matters. So the way we take this uncertainty into account, we just want to predict the value of y star given the data and x star, where we've integrated out the dependence upon the unknown parameter psi. Yeah? So I'll show you how to do this in a minute, but let's just have a look at whether it's worth doing. Okay, now I think it varies whether it is, but there's one just particular example to say why it might be worth doing. I've just generated some toy data here. So I just generated it from a Gaussian process with this setting for the parameters with a squared exponential covariance function. So we've got these points. Okay. So I then estimated the parameters using the map estimate, so the maximum a posteriori estimate, and this is the fit we get. So the solid red line is the posterior mean. The dashed line are the 95% credibility intervals. Okay, so that's your standard kind of Gaussian process fit. So if we look at that, there are a few things you might comment on. First of all, there's no uncertainty here, look. We're pretty much certain, the Gaussian process is pretty much certain what the true value of the function is in here. And same over here. So that's a little bit odd. This is a little bit strange as well. I'm not quite sure what's happening, but I think it's because I've got a squared exponential covariance function, which is a true covariance function. The data really come from this model. So I think because this is slightly arching up, to get the gradient right, we've got this slightly strange peak. And perhaps over here as well, this is a bit odd, that the uncertainty, the mean function goes back to 0, but the uncertainty doesn't go anywhere either. I might expect it to come down here a bit. So let's look at what happens if we integrate across the uncertainty in the parameters. Remember, I've just fixed them here, and we've got a plug-in estimate. So you have to adjust your eye to this. The black lines are what we get if we integrate across the parameters. Okay? So the red lines are exactly the same as before. The black lines are the value if we integrate them out. So now, I hope you can see this, we've got uncertainty around here because when we integrate across the range of parameters we get a range of values. We've got more uncertainty in here. We've smoothed out this a bit so we don't have this weird peak to try and match the gradient. We just miss the data points a bit instead, and the uncertainty grows off down here as well. So to me, in this case, it looks like it's a worthwhile thing to do if what you really care about is the uncertainty. To me, the map estimate looks a bit artificial. So I think it's not always the case that plug-in estimate is good enough. I think there can be cases where sampling across the parameters is useful. Okay. And just to know as well, this is using the true covariance function. So in a situation like Philip had in his talk, where he generated data from a rational quadratic covariance function and then fitted a squared exponential, so the model's misspecified, this could be even more important. Yep. I think if you've got a misspecified model, taking into account the uncertainty from having estimated parameters can make even more of a difference. Okay.
How close was the ML estimate to the true value?
It was pretty close. Yeah. So I should have written it down, but I think it was something like 2.23, and this was way too small. That's the problem here. So it estimated the nugget parameter, the variance of the observation to be too small. This was 0.0001 or something. And that's not uncommon, I think, if you're estimating all these parameters to have to find that the best supported values are ones with a very small, so you're nodding, yeah. So I think this often happens with Gaussian processes. And perhaps you'd have got better fit if I'd used cross-validation rather than maximum likelihood, but it's a straw man to knock down, right? Yeah, Jeremy?
So for example, what sort of prior are you using for hyperparameters? Were you saying the function can really look like anything in terms of...
No, so if I remember off the top of my head, the prior for Tor was exponential mean 1. This was gamma and gamma with, I think, mean 10 and 10 in both cases. Yeah, so they're informative priors.
So are they, values, are they constraining the function to be fairly smooth, or are they saying the function could wiggle over the place?
Say it again, sorry.
Well, I can't quite picture it. So were the priors constraining the function to look reasonably smooth? Or were they
yes, they were. They weren't. They were saying the length scale was somewhere between 0 and 100 were the only feasible values. The variance was a simile, and that the nugget term wasn't massively large. It was constraining it to be small. Philip.
It's just a question to the entire room, but mostly to you. This is something that I've noticed before, sort of in sort of hard problems like this that you might do for sort of demonstrations. That the length scale and this tau spread, the observation noise, are actually, they're sort of correlated variables. I'm not saying they're unidentified, but there's some kind of something going on between them, because you can either have no noise, then the function has to be very bendy, or you can have lots of noise and the function can be very smooth.
Yes.
Is there any kind of formal thing known about this? That these two parameters somehow relate to each other, and there's maybe a better description that links the two, or anyone?
It's not uncommon, so related to your point, to get a fit that is essentially a straight line with a very small nugget, a large nugget and a very small length scale. So at the data point, you just zip up and down to it. That's not an uncommon thing to see. So you know you've done something wrong, but
in that case, I think there's in that case there is an identifiability problem, and I think that if you start making the length scale shorter than the smallest point distance between your points, then as far as the model is concerned, the exponentiated quadratic and noise term are identical. They're non-identifiable. In fact, the noise term has an interpretation as a very short length scale.
Yeah.
In fact, I often think of it like that.
But this is
for the longer one, the other way around, just sort of saying.
So the short length scales are, I mean, they should just be suppressed by the likelihood, because it just makes the model extremely flexible. But having
maybe I mean long length scale with large nugget. That's what I mean. Yeah. I mean, you can pick these things up normally, and normally you wouldn't have to estimate this thing. Like in most cases, you have a good idea what the observation variance is. So I've set this up to fail in a sense, but I don't think it's that unusual a problem.
No, I think you're right. I think that it's very similar to. Well, the problem I showed you is a real data example where I should have sampled in my first talk. So I think that's nice to show the sort of effects you can.
Yeah. I mean, I think if you put improper priors on, it might. There's a whole other kettle of set of problems you get. These are proper priors. So how do we sample these hyperparameters? So I know the Laplace approximation is very common in machine learning, but statistically we always tend to resort to sampling, or I do anyway. So the default kind of method is Metropolis Hastings, MCMC. So the idea is there you want to build a Markov chain on the parameter values that converges to the posterior distribution you want.
We never do Laplace approximation.
Do not? Okay.
Because it's so non-Gaussian.
Okay.
I think, well, no one I know does it.
Didn't you and Mike just have a paper?
You did. Mike Roman and I have a paper recently that showed this. You should not marginalize over the Laplace approximation. It's actually surprisingly good.
Did you ask me?
So there are Laplace approximations. Let's see Philip's work.
So only Philip does it. Philip does it.
And Mike and Roman.
Okay, so I don't want to talk about this because I don't think this works very well in a lot of cases. This is a random walk Metropolis Hastings, so I've got a local move on the parameter, say a Gaussian random walk, and you accept or reject your proposals. Yes?
So can you just clarify whether you mean hyperparameters or whether you mean weights?
I mean hyperparameters, so I mean the things you have to specify for the covariance function is what I mean, yeah, thanks. So you can tune this, and you can spend a lot of time tuning this and making it work a bit better. Okay. But it tends to mix very poorly. And I'll show you a simple demonstration of it mixing poorly in a moment. So there's two approaches that tend to be thought of as working much better, particularly in Gauss's process hyperparameter estimation. One is HMC, Hamiltonian Monte Carlo, and the other one is slice sampling. So if you don't know about slice sampling, it's very cool. So Jeremy told me yesterday that someone had told him that the only people who use Metropolis Hastings are those people who don't know about slice sampling. And I didn't know about slice sampling until 6 months ago, but now I know about it. It works much better than everything I was doing before with Metropolis Hastings. So the idea with slice sampling, I apologise, the notation's changed because I nicked this from Wikipedia. So x is now the variable we want to learn over, and d is our data. Okay? So x and psi have just switched for a moment. So the idea is you want to sample from this density function, and instead of trying to sample from this density, we instead introduce a new density, which is we want to sample from the uniform distribution on the area underneath this curve. So we introduce a variable y, okay, and we want to sample x and y jointly such that y is less than f of x, where f is the density or the unnormalized density we want to estimate. So the area under here. If you think about why this works, if you marginalize across y here, so integrate out y, if we wrote an integral sign, wrote dy in front of here, you're just going to get f of x back, the density you want. Yep. So the slice sampling is very simple. What we say is if we're currently at x0, we uniformly sample on this height a value of y, so just uniformly pick something between 0 and f of x, so maybe here, and then we uniformly sample along this slice. Okay, and there are ways of doing this uniform sampling along here, and you have to tune a little bit, but generally you move around this space much better. Okay, so this is a Radford-Neal invention. I can't remember the year, but so again, just my simple demonstration to illustrate what happens. This is the trace plots from slice sampling on the top and Metropolis Hastings along the bottom. Okay? So there's 5,000 iterations at the top, 10,000 iterations from Metropolis Hastings, so there's more. And I apologise, the axes are slightly different here. The axes are larger along the top, so we've got much better mixing. Not only do we get stuck here, we're not exploring the same range. So this goes from 0 to 40, this 0 to 20, and 0 to 0.6, 0 to 0.25, and so on. So this is typical of what we see in Metropolis Hastings. We get stuck in the same place for a long time. So just to look at the posteriors as well, so these are the marginal posteriors, and I apologise because we're on different axes again for the 3 parameters, but I couldn't put them on the same axis because this is so terrible. We never really got away from 0 here. And so if you just done Metropolis Hastings, you'd have got a fit that looked like the plug-in estimate, because this is too small again. So that was exactly the problem with the maximum likelihood estimate, the maximum likelihood estimator, whether the true value or the optimizer got stuck near 0. Metropolis Hastings got stuck near 0 as well, whereas Slice is done pretty well. The posterior is near the true value. So I'd never done this before till yesterday. I just thought it was informative, and given what people had said, I thought it was worth including. Okay. So are there any questions about that? I'll move on. Yes?
Have you compared this with Hamiltonian Monte Carlo?
No, I haven't, but Ted uses Hamiltonian and Monte Carlo, right? And
I'll know next week.
okay, Ted will know next week, so I'll ask him next week. So
Come back next week. Or reconvene.
Asking people who know more than I do, my impression is that they're if you know nothing about the problem in advance, it's hard to pick a winner. But any given problem, I mean, someone's nodding, you might know more than I do, but for any particular problem, HMC might outperform Slice or vice versa, and I don't know what works best here. I know some people use HMC for these problems, but it varies. Yeah.
Do you then guess how either of these scale with dimensionality?
Well, nothing scales that well with dimensionality, right? But I don't have any idea now off the top of my head. No. Sorry.
Just on this the Hamiltonian thing, I think it might have a problem with strongly multimodal distribution.
Right.
That slice sampling might not.
Right.
So that's something to consider, especially with what you were saying before.
That's my understanding as well, I think. Yes.
I had a question. Oh yeah, no, I wanted to ask, are you arguing that slice sampling is great in general, or specifically because of the nature of GP?
Probably both. I think I'm not arguing from any great experience. I'm arguing from having read people, Radford-Neal, who claims it works well in GPs. So yes, from my understanding, from talking to the Monte Carlo hardcores, they seem to think slice sampling works well in general, much better than Metropolis Hastings. Yeah. You.
You have a lot of parameters. For each parameter, say you use slicing Monte Carlo, you introduce auxiliary variable. Then you introduce a lot of auxiliary variables. Will that possible?
You only need one auxiliary variable. Was that your question? Did you say you need lots of auxiliary variables?
Because you have a lot of parameters.
No, you only need one because.
Can you repeat the question?
Yes, sorry. So Mew's question was, if we have a high-dimensional X or a multi-dimensional X, do we need lots of auxiliary Ys? The answer is no, we just need one Y, because this becomes a volume rather than an area. There's still only one height to this volume, yep, so there's still only one auxiliary variable. Yep. Yeah.
So I had a question about parameterization. So you've parameterized it with the variance for the signal and the variance for the noise, which I think is what I do most of the time.
Yeah.
But you could, in the example we had, the one where I showed the multimodality, we'd actually parameterize with a signal to noise ratio,
right,
and an overall scale. And I wonder about that, because the overall scale, I think, is quite well determined, relatively speaking, as you increase the number of data. You see that in the T-process thing that Jeremy mentioned yesterday, that the T-process actually, the degree of freedom scales with n. So once you've seen even 10 or 12 data points, often you've got a good idea of the overall scale of the data. So is it sensible to be throwing that in as a parameter shared between the noise and the variance? Is that maybe relating to this correlation thing? Is that causing some of these funny correlation effects?
I mean, generally with MCMC, reparameterizations help massively. If you find a good one that decorrelates your variables, it's going to make a massive difference. And so if what you're talking about decorrelates things, then it probably will help.
So has anyone ever done that here? I mean, someone's done it. No one experienced sampling where you reparameterize as a scale and then a signal to noise ratio. No. Okay. Right, that's my idea, by the way.
The other thing I forgot to say is that the choice of prior, I mean, Jeremy talked about this yesterday, helped massively. So you don't need to sample across all these parameters if you set up the problem in a conjugate way. So if you pick a conjugate prior, an inverse gamma prior for sigma squared, you don't need to integrate across it, and there's probably a conjugate analysis for tau squared as well. I'm just doing this for illustration purposes. Yeah. So in practice, in this problem, I would only integrate across lambda, the length scale, probably. Okay, so I'm going to come back to the sampling, and I'll do it sequentially later, and you'll see Neil's point that you learn very quickly what the length scale is. But to do that, I just want to talk about why it might matter, so a problem to motivate it a little. So I'm going to talk now about calibration. So calibration is estimation of parameters. Okay? So typically we build forward models. So someone comes along with a simulator, f of theta, which generates an output x, and we want to compare the output x of the simulator to the real data we observed, d, to learn what the true values of the parameters theta were. Okay? So this is the problem from my PhD thesis. We want to know, when did the primates evolve? When did they first appear? So we have a model of evolution, so we start off with one primate species and it branches into multiple primate species, and we have data, which is fossils and some genetic information from the top, and that's a forwards model that simulates forwards from this start point, and we want to go backwards to say when in time did the primates evolve. Okay, so it's an inverse problem. So as Bayesians, all we want to try and do is find this posterior, the posterior distribution of theta given the data d. Okay. So what Neil mentioned in his introduction was there's a class of methods called ABC methods, Approximate, Bayesian, Computation. And the key thing about ABC methods is they don't require knowledge of the likelihood function. Instead, all inference is done using simulation from the model. So as long as we can simulate from the model in a forwards fashion, we can do inference. Okay. And these methods, I mean, just a quick show of hands. Who here has come across ABC before? Okay, about a third of you. Okay. So these methods have become big news in the biological sciences. So if you work in genetics, epidemiology, and so on, these methods are almost the first port of call for a certain class of models now. They've become increasingly popular. And the key thing to know about them is that they sound very crude, and they can be very crude, these methods, but they have a really important role to play. And that the scientists in pretty much any community are building simulators and fitting them to data. Yep. And although they might not be very good at statistics, they're very good at modelling. They know a lot about their problem, and to do the inference properly, they're going to have to know a lot of statistics and a lot of probability theory and be able to calculate the likelihood function, then know about a proper Monte Carlo sampling scheme, so MCMC or something, and that can be very difficult. You need lots of expertise and statistics to do that. So ABC is kind of a very simple class of model that can be used by anyone who knows how to build a simulator, at least the simplest form. Yeah? So for that reason, they're popular. And so for that reason, we should study them and try to improve them, I think. So what is ABC, if you don't know what it is? So remember, we're trying to sample here from the posterior distribution of the parameter theta given the data D. So the way the algorithms work is very simple. We start by picking a theta from the prior. We then simulate some data from our simulator using that value of the parameter. And then we accept the parameter if the difference, the distance between the simulated output and the real data D, x and D, is small, where we measure small by some metric and some tolerance. Okay. And that's it. That's the entirety of ABC, essentially. So to understand how this works, if you imagine epsilon's infinity here, well, that just says accept every single value of theta. Yep. Every time we're going to accept, because we're always running distance infinity. So if we accept everything, we're just going to get the prior back again. Yep. If we imagine epsilon 0 here, we're only going to accept if D exactly equals x. And in that case, it's very easy to show that what we get out is exactly the posterior. We get samples from the posterior distribution. Yep. So if epsilon's small, we have a very accurate algorithm. We get the posterior back. If epsilon's large, we have a very inaccurate algorithm. We get the prior back. So as you can see, if epsilon's large, we're going to accept a lot. We're going to get the answer very quickly. If it's small, we're going to be accurate, but we're going to have to do an awful lot of simulation to get enough matches to be able to allow us to characterize the posterior. Yep. So epsilon kind of reflects this tension between computability and accuracy. Okay. And there's kind of been a cottage industry in ABC in the past decade of creating ABC versions of every algorithm you've ever heard of, basically. So there's every sampling algorithm. So MCMC, SMC, EM, EP, and so on. Yeah. There's an approximate Bayesian computation version of everything you can think of pretty much now. Okay. So I just need to generalize it a little bit to tell you, before I can introduce how Gaussian processes are useful here. So we can show that, we can generalize ABC. So we do the same as before, we pick a parameter theta from the prior and simulate an x from the simulator. And now instead of accepting with probability 0 or 1, we're going to accept with some other probability that has this form. So we're going to introduce some way of relating x to D and accept with this probability. Okay? So this isn't very important for what I'm about to say, but just note it's not 0 or 1 anymore, it's smooth. Okay? And so to see this is a generalization, if we let this be 1 or 0, depending on whether x is close to D or not, we get back exactly to the previous page, the previous slide. Yeah? If 1 or 0, that probability becomes 1 or 0, and we're back to this. So this is just a generalization, and it's an important generalization because it makes this acceptance probability a smooth thing rather than just 0 or 1. And 0 or 1 is very difficult to model with the Gaussian process, where smooth things are easier to model. Okay. So, at least some people in machine learning tend not to like Monte Carlo algorithms. Okay? So I think Zubin Garamani wrote a paper saying how Monte Carlo isn't a Bayesian procedure. And it's a bad procedure for the following reasons. We don't learn from previous simulations. Okay? We throw away information we've learnt. If we sample once at theta and we return to theta later in our MCMC, we sample again. Yeah? We haven't learned from what we did previously. Okay? We also don't exploit properties of the likelihood function, such as continuity. We know that, for most models, we know the likelihood function is a smooth, continuous function. And Monte Carlo algorithms don't assume this. They learn it from scratch. Okay? And so that's expensive. You've got to put in effort to learn that smoothness. And we do other things like sample randomly rather than use space-filling designs. So Monte Carlo algorithms are great in that they're guaranteed to work if we run them for long enough. They're bad that they can be inefficient in these ways. Okay. So if we're prepared to lose this guarantee of eventual success, we can perhaps exploit the continuity of the likelihood function to learn quicker about its shape and to get to the answer more quickly than we might just using pure sampling. Okay, how am I doing for time? Okay, so the last slide before Gaussian processes return. So in kind of the generalized ABC framework, we've got some way of estimating the likelihood function. This is what we assume we don't know in ABC, but we have a way of estimating it, and the way of estimating it is to sample x's repeatedly from the model and then to sum up these kind of terms. So if this was 0 or 1, this would just be the sum of the number of times we accepted. That's all it would be. Okay? So again, the details are important. Just know that it gives us a way of estimating what the likelihood function is, a noisy estimate of the likelihood function. Or, for those of you who saw Simon Wood's paper in Nature in 2010, he does essentially the same thing, but what he does is he assumes that this density is Gaussian and estimates the moments instead. Yep. So there's a different kind of assumption. So the key thing is, if we think the likelihood function is smooth and continuous, that if we estimate pi of d given theta, then it should be similar to pi of d given theta prime when theta prime is close to theta, yeah? If it's smooth and continuous. So we can begin to model it. It's the key thing. We can potentially use Gaussian process models to start to model the unknown likelihood function and then use the Gaussian process model in our inference. Okay, so let's see how this works. Okay, so this is my toy example. So this is a very simple model from ecology. It's the Ricker model. Yep. But it's perverse, so it tends to be used as a pathological example to test your sampling algorithm on. Yep. So the details don't matter. So the key thing to know is that there are 3 parameters in my problem here. We've got an R, a sigma, and a phi. Okay, we're going to learn the posterior distribution of those 3 given some data. Okay, so we'll do everything with pictures. Yep. So what we're going to try and do to do the posterior inference here, we've got 3 parameters, R, sigma, and phi. And so I start by defining what their prior region is, and then I have just used the space filling design to populate that region with points. Yep. I projected them onto 2 dimensions here, so that's just a projection of a 3-dimensional sample onto 2D, each of the 2D projections. And at each of these values, I estimate the log likelihood by running the simulator a number of times, so 500 times, I think, here. Okay. And what we're going to do, once we've estimated the likelihood at each of these values, we're going to try and fit a Gaussian process model to it. Okay. So we've got an estimate of the likelihood at each point, and we're going to take the log to get an estimate of the log likelihood. So the first problem we have is that the log likelihood function varies very widely. So even for this simple problem, the Ricker model, where I've restricted the space down to a fairly narrow range, the log likelihood varies from about 10 to the minus 5 to about 0. So modelling any Gaussian process over that kind of range will be very difficult. Okay? So what we want to try and do is cut out bits of space that are implausible. So we're going to use kind of a sequence of models and try and build them ever more accurate, and with each model we're going to try and rule out bits of space as implausible. Okay, so I'll show you in pictures. Okay. So this is the first design. Take this design, I fit a Gaussian process. Okay. This is actually a fit to the negative log likelihood to make it even smaller. And what we say is that if the value of the log likelihood is very small, very negative, and it's flipped upside down here, we're going to rule that value of the parameter out as implausible, because in the posterior it's going to have 0 weight, essentially. So these are just diagnostic plots. So all I've done here, I've picked the value of the parameter, taken a slice through the parameter space, and the red line is my Gaussian process fit, and then I did some extra runs just to check it was working, and that's the black line. Yep. And anything above the blue line up here is ruled out as implausible. So here it looks like we've just ruled out this bit of parameter space, so R can't be that small, this particular slice. Okay. So we use the bit. So what we've done by this first Gaussian process is rule out a bit of space as implausible, as it couldn't possibly have led to the data. So here, it doesn't look like it. We've ruled out 38% of space here because this is a projection from 3 dimensions onto 2 dimensions, so it looks smaller than it really is. Yep. So we put more points in the bits of space we haven't ruled out, rerun the simulator, fit a new Gaussian process. Yep. So it's another slice through. So the red line against the Gaussian process. So you can see we're doing okay. We've got the general shape, but we're not doing very well over here. So what we're going to do, we're going to cut off the bits that are really bad down here and throw them away as implausible. Okay. So now we cut out 62% of space, put more design points in. And so what we're doing with each of these iterations is we're cutting down the bit of space, the range of the log likelihood function. So to begin with, it was from 0 to 10 to the minus 5, 10 to the 5, minus 10 to the 5, sorry. I don't know what the range we cut it down to here, but we cut out, the tail of that. We cut out the worst bits of space. Fit another Gaussian process, rule out more space. Okay. So this is the last iteration. We've got 4 different Gaussian process models. After doing this 4 times, we've got this just 5% of space left. So remember, 3D projected to 2D looks larger than it really is, so this is just 5% of space left. And now, in this interval, in this range, the log likelihood doesn't vary that much, and we can fit an accurate model in this interval, in this region. Okay. So once we've got our accurate Gaussian process model, we just run whatever our sampler is to estimate the posterior. And so what we've got here is an estimate. The black line is Simon Wood's estimate of the posterior using his code, and the green line is our estimate using kind of a Gaussian process to help speed up ABC. Okay. The key thing is the amount of computation we've required. Okay. So Simon Wood's code, the Wood code used 10 to the 5 times 500 simulations. We only used 10 to the 3 times 500 simulations. So we've only used 1% of the amount of computer power to get pretty much the same answers. Okay, there's some difference between those answers. So essentially all we've done, we've got we've used the same routine as Simon Wood, but rather than just throwing away iterations in his MCMC sampler and re-estimating them each time we come back, we've fit a model that remembers where we've been and remembers what we found last time. That's essentially all it amounts to. Okay. So these ideas have kind of, I think their time has come in a sense. So Max on the Ted and Max, Ted on the front row just put a paper in the archive last week. I put mine in the archive last week. So Ted had a very similar idea, whereas instead of modelling the log likelihood function like I was doing, he's modelling the first and second moments of the simulator output, okay, and doing essentially the same thing. So I think there's differences between these things. In this approach, we only have a one-dimensional object to model. But it's very difficult because the scale varies so much, so I have this iterated wave thing. Whereas Max's approach is much easier to model the mean and variance, but these are both multidimensional things, and then you have to have some kind of assumption for the likelihood. So if you have a Gaussian likelihood like Simon Wood did here, you get into difficulties again. Okay. So I think there's different cases where these will work differently. Then there's other non-ABC kind of Gaussian process accelerated papers. So in November, Darlin and Linston put a paper on the archive using GPs to speed up parameter estimation in state space modelling. Carl Rasmussen and Telson 3 had one to speed up Hamiltonian Monte Carlo, and I'm sure there are lots of others as well. Okay. These things, if you can get it working, they really do save you computational effort, I think. But it's a very young thing. Okay. Okay. So, any questions about that?
And this is why the likelihood is harder to do than the log likelihood.
Why? Because the likelihood has to be positive. Yep. So if you fit a Gaussian process model to something, the likelihood function has got to be positive everywhere. and it's going to be 0 a lot of places, and I can't constrain a Gaussian process to be positive. We don't know how to do that. I think that's, yeah. So if we knew how to do that, perhaps I could use, perhaps I could model the likelihood itself, but I can't, so I model the log likelihood. Yeah.
Yeah, Archivatari has a trick he's been using for that, where when it goes negative, you make like sigmoid observation that it's positive. You like introduce a classification observation that it was positive.
Right.
Which I think is nicer than other people have tried things like that, but that's, I don't know. It's a nice idea.
Yeah.
We haven't tried it, but we're excited to try it.
Right. Yeah.
He was using it for monotonic functions actually, so he was using it to force the derivative to be positive to make a function monotonic actually for a survival model, which, but implicitly it's the same thing, isn't it?
It'd be nice to be able to model the likelihood, because we know that our estimate of the likelihood is a Monte Carlo estimator, so we know the variance of it. Yep. Or we can estimate the variance of it. Whereas when I take the log, I can no longer. It's not so easy to know what the variance of a log of an estimator is. So it would be nice if I could model the likelihood instead. That would make life easier. Ted.
Well, the modeling the log likelihood makes a lot more sense too. It's like, because if you take the uncertainty on the log likelihood and then you exponentiate it, you get the uncertainty in areas where you have mass, but then the uncertainty goes to 0 rapidly.
Yeah.
Away from.
Yeah, that's exactly it.
Mass, so
yeah.
You get much more plausible variance.
In the quadrature community, and if I can sort of try to channel Mike here a little bit, they also model logs for the same reason. And as you said, then another nice property of that is that you really get a function that is almost 0 almost everywhere, and in this very asymmetric kind of way.
Yeah.
That is good.
Yeah. Yeah, so I think that's right. I think even if we could model the likelihood, we would probably still choose not to. It just makes life difficult for us in some ways. Okay.
Generally, where are you? I confused you. You're hidden behind here. In prior elicitation, you sort of put these, you model the likelihood directly, right? Model the density function, so you model the value of the probability rather than the log value.
Yes.
But then they deal with the problem, I think, Ted, and you can correct me if I'm wrong, you then multiply the whole thing by a Gaussian function to force it to go to 0 outside the domain, which deals with the issue Ted's worrying about, that as you go to 0, you get high variance. But if you multiply your covariance by a Gaussian itself, then it actually pushes everything down outside the regime, and that's how I think that's how you do it in, which is another.
Yeah, it seems unnecessary.
Well, I don't know. It could be, but it might help actually with the thing that Rich is talking about of what if you were to use multiply, equivalently that would involve multiplying everything by a quadratic, which might give you this behavior that I actually think everything goes flying off down from the quadratic rather than the non-parametric part, which might be helpful.
So I do put in a quadratic mean function to try and make sure that in the tails of the prior region we get the log likelihood going to 0, or minus infinity, sorry, which is an assumption about the behaviour of the problem, that the mass is in the interior.
It's the same thing because it's log additive, isn't it? So it's like multiplying by a Gaussian.
Yeah.
Of course, yeah.
Okay.
Yeah, I mean that's actually one of the good examples of why you would want to have a mean function. You could just simply put your log prior as your mean function, and then you're just modeling the likelihood after that.
Yeah, because of log additivity,
Yeah. Okay, so I'll finish on this. I've got a few slides on. It's not really active learning. That's just the motivation for doing it. But on what happens if we have data that arrives sequentially. Okay. So if we have n data points, we want to predict tomorrow. We then observe tomorrow, so we have n plus 1 data points. We want to predict the day after that, so we have n plus 2 data points, and so on. So if we have data that arrives 1 point at a time, and we want to repeatedly predict ahead, then we need some way of sequentially learning things. Okay? So the reason this arises is that in this ABC, GP ABC work, I'd like active learning. Rather than what I'm doing at the moment is just putting down lots of design points, I'd like to be able to choose my next design point. Sorry, theta is changed to x now. I'd like to choose it using some heuristic. Okay? So use a Gaussian process with my current knowledge to say where is the location in parameter space that would be most useful for me to run the model. A bit like Philip had in your talk this morning. Did you talk about this morning? I think I'm remembering your talk from the summer. So either this morning or 6 months ago you talked about this. Okay. Which is only useful to me, of course. Okay, so we use the Gaussian process to say where we're going to run the simulator, and then update using this new design point. So how do we do this efficiently? Well, in order to answer that, we need to think about what a Gaussian process, a trained Gaussian process, what information is important to know. What do we store when we have our Gaussian process? In GPy, what is the information that's being held in memory in order to help you make predictions? Well, there's several things. One thing that's stored is the inverse gram matrix. So this gram matrix is the covariance between all your design points. We've got this matrix and its inverse, they're stored. Yep. We also have estimates of the hyperparameters stored. Yep. So they're the key things that we have to keep in mind for when we predict ahead. Okay. So suppose now we're giving a new observation pair, new x and y, that we want to incorporate in our GP training set. How do we update the Gaussian process? Well, we add a row and column to the gram matrix and then do the new inverse. Yeah? If we do this naively, this has cost order n cubed. Right? And so if we have a cost order n cubed each day, that's going to get expensive very quickly. So I don't think anyone talked about this week, but I thought it would be useful just to have it in. That instead there's a much more efficient sequential matrix update equations. Okay? Which I think, are they in GPy yet?
No.
No, they should be. It makes a massive difference.
Daniel Sharto, who's around somewhere, did a lot of work on these in machine learning a while ago, yeah.
Okay.
Good, yeah.
So we've got kn-1, the old gram matrix. When we get the new design point, we add a row and a column. Yeah. And there's an efficient way of finding the inverse of kn, so kn inverse, if we already know kn-1 inverse. Okay? So the formulas don't matter, just know that these equations exist. Yep? That if you know the inverse of using the n-1 design points, it's cheap or cheaper to get the inverse with n design points. Yep? And this has cost order n squared rather than order n cubed. Yep? So you add a data point at a time, obviously that adds another n, so we get back to order n cubed. So we're not saving anything in the grand scheme of things, but if we're doing sequential predictions time after time, the savings soon adds up.
In fact, they are in effect because they're needed for EP.
How are they?
So when you do EP, you remove a point and re-add it. But it's just reminding me as well. I mean, they're in there for EP for that reason. But you have to be careful about how you do them. You should do Kolesky updates. I think is better, more stable than if you do the Sherman, Morrissey, Woodbury implied ones. And I like the fact that Philip's nodding, so I'm going to say that more confidently.
You should do Kolesky updates.
Yes.
Matthias Sieger has a paper on
he spent a lot of time. Kolesky downdates and updates were actually, because in EP what you do is you remove a point and then re-add, and the remove is the particularly unstable. Maybe it's not so important for adding. Like, so if you want to throw away a point, forget it, then that can be very unstable.
Yeah.
But there is so maybe you'll talk about this in the next slide, I don't know, but there's this, I've never actually tried this, but people have mentioned to me that if you do this, and I had a discussion with someone in the web blog yesterday, that if you keep on doing this sequentially, that there's a bad accumulation of error. I remember Carl Rasmussen wagging his finger at me for trying to do this repeatedly. So if you do it once, it's obviously a very good idea.
Yeah.
If you do this 1,000 times, don't you have horrible error propagation problems?
I didn't for 1,000, but in the algorithm I'm going to use it for, I'm going to replenish every so often and do it from scratch because of the sampling where I'm doing it. So I kind of use the sequential bit for 20 new data points or whatever, and then I recalculate from scratch. Because I want to re-estimate the hyperparameters as well.
EP implementations all have to do that as well. At some point.
So error does accumulate. I didn't notice the error accumulating here. Okay, but you get massive time savings, right? This is just for 1,000 data points. In my naive thing, if you're predicting 1 day ahead for 1,000 time points, it soon adds up. Yeah, these errors. So what do we do with hyperparameters here? So the simplest naive thing to do is keep them fixed and then update them after, say, every m new data points. Yeah? So you just keep them fixed for the next fortnight. In 2 weeks' time, I decide, I've got enough new data to make it worthwhile re-estimating them. Let's do that. Okay? And we can use the current value in our optimizer as the start point to help guide, but they probably haven't changed that much unless you've changed regime. Okay? So alternatively, I'll just very quickly go over it, is to use sequential Monte Carlo methods. Very last few slides. I know these really aren't popular, at least from Neil.
Bootstrap isn't popular, but in general they're okay.
Okay. So, just so I know, who is familiar with particle filtering or SMC algorithms? So, a small number of people, okay. So the idea is that we represent our posterior by a cloud of weighted particles. So we've got a number of particles, so theta is like size my collection of parameters, and each one has a weight. And I'm going to approximate the posterior by a weighted sum of them, okay. As each new data point arises, as we get a new point in D, all we're going to do is update these weights. And so that's going to, the cloud of particles somehow spans our input space, our prior space, and we're going to update the weights to update our beliefs about the parameters as we get more data in. Okay. So what is the information we need to carry around for Gaussian processes? Well, our data that comes in are the pairs of x and y's, the inputs and the outputs. The particles that we're going to need to carry around are the hyperparameters themselves and the gram matrix, or the inverse gram matrix, so that we can use these sequential inverses. Okay. So let's give the algorithm at the same time. We're going to exploit this relationship. So what this relationship says is if we have a belief about the parameters at time n, when we've got n data points, so that's our current posterior belief about the parameters, there's a simple way of going from the belief at time n to the belief at time n plus 1. And the way to go from time n to time n plus 1 is through these two steps. Okay? So the first step is this is a particle learning algorithm. This is a resample step. So it says, what's the probability of the next data point given the current values of the Gaussian process? And that's very simple. That's just the prediction of y at the new x. Yep. So given our current particle, our current hyperparameters, and we've got a cloud of these, we just see what the probability is of the data point at the next point. And so we give all the particles these weights, then we do the update step, the propagate step, which is just to update the parameters in light of this. So that's just the gram matrix bit I had before. Okay. So if you're not, I'm going very quickly here, but it's just two very simple steps. This is just standard Gaussian process prediction. This is just the matrix inverse, the sequential matrix inverse I had before. That's it. Okay. So what we get is a sequence of distributions for our belief about the parameters. So I've just picked out the length scale parameter here. So it's the same data set as before. So we started at time 0 with our prior. This isn't actually time 0, this is time 1 or 2, I think. We have some belief after having 2 data points. We had a data point, we picked the head, we update those beliefs, predict the head again, update them again, and so on. And all we're doing each time is just reweighting all the particles. And so what we get at the end is the same answer we'd have got if we did MCMC, but we've done it sequentially without having to ever run an MCMC sampler.
Yeah, so now every time you introduce, you store a covariance associated with every particle, but because the particle set's fixed, that's why you benefit from the sequential update on the inverse.
Yep.
That's clever, yeah.
Yep. So there's a proviso. Okay, I'll give you in a minute once I show you the answer. So these are the posteriors. So this is with 100 particles. So the black line was from slice sampling for the 3 different parameters. The red line was for SMC. So it's not perfect by any means. There's only 100 particles here. This is 1,000 particles. So we're doing much better. We're pretty close now. You can see there's some degeneracy problems. So we get these bumps in places, but we've done pretty well. So with only 10 or 20 data points, it's not going to make much difference. But as soon as we're into kind of the regime of 100 or so data points, it becomes much more efficient to have these sequential approaches than it does to run a slice sampler. Okay, if we want to make predictions each day, that is. Okay. So just go back and I'll finish. The one proviso of this is that particle filters suffer from degeneracy. Okay? We've got this cloud of weighted particles, and degeneracy occurs if we end up with all the weights being 0 apart from one particle that has weight 1. And that's saying we've reduced our particle set just to a single particle. Everything else is unimportant. And this can happen quite quickly. Okay? So we measure degeneracy with something called the effective sample size, and the effective sample size is n if we have an equally weighted set, and it's 1 in this case, and it tells us kind of the equivalent number of particles we have, the amount of information we have in our thing. So we monitor this, and if this drops too low, we do particle replenishment. So particle replenishment is where we move the particles. Okay. So Neil's question a moment ago is that we're keeping the hyperparameters fixed, and we're just doing the matrix inverse. So if we drop down too badly, here we have to run a slice sampler or some Metropolis Hastings sampler to move the particles a little bit. Yeah. So in these results, I think I had to do this twice. Somewhere around here and somewhere around here, the effective sample size dropped below. I think I had a threshold of 90%, which is unreasonably high here. I should have a 50% or something. But yeah, you do have to do this every so often, so it's not entirely rosy picture. Yeah. But I think for sequential problems, these sequential Monte Carlo methods can make a big difference. Yeah. Okay, so I think I'll just finish there. I didn't have any conclusions at all, except given there was no unifying theme to my talk, it's hard to have conclusions. Other than that, Gaussian processes are cool, right, and we can do good stuff with them. Okay, so thank you.
That's great, because that's supposed to be the workshop, the summer school conclusion.
Is it? It's just useful, yeah.
GP's cool.
Yeah.
Do fun stuff with it. Okay, questions?
Yeah, this has been a nice workshop, and at least you have succeeded in converting me into a GP enthusiast. I would have a question. So, do you think you should and could you use a model choice criteria to distinguish between the GP models and non-GP models?
I think that's a question for you, isn't it?
So could you say it again? Sorry, is your question? Use the model.
Use the model choice criteria to distinguish between, let's say, different kernels, and also between GP models and models where the kernel is essentially a delta V.
So Zubin Garamani talked about this at NIPS, didn't he? So he had he called it an automated statistician. He's trying to do me and Jeremy out of our jobs. So he had a collection of covariance functions. He fit them all, and he basically wanted to then do model selections and choose in between them. I don't remember the name of the work or the first author, but
it's related to David Divanau's work, isn't it, on these grammars of covariance functions?
Yeah.
And that's very interesting. I think that's we haven't actually talked a lot about estimating marginal likelihoods and model comparison, which is probably what drives the question, but it's something we probably should have talked about, comparing different GP models or other models using the evidence, or what the Bayes factors, the ratio of the marginal likelihood to others is considered a good way to do that. And when we work sometimes in computational biology and medical stuff, people really want to see p-values. They really want to see your p-values, and then you can just go to likelihood ratio tests using the marginal likelihood as your likelihood.
I mean, so two comments here. I mean, you can. So back to my one of the early slides about being a good Bayesian or not. So you can use this marginal likelihood, right? You just ignore the prior bit and ignore this bit. So you just plug psi hat into here. This gives you an estimate of the likelihood of your data given that one particular choice of the parameter value. So that's one thing you could compare between different covariance functions. Better would be to compare this quantity. I mean, ignore the ones, the stars. So the probability of y given x, where you've integrated out the uncertainty in in psi, and that's hard to get at, but you can, the particle filter, the SMC methods, automatically give you an estimate of that quantity if you record the weights as you go through. Okay, it's the product of the sum of the weights. So you can estimate these things, but the estimators tend to be very noisy, not particularly well behaved. So it depends really what you want to do. I like the cross-validation approaches where you just have a test set and see what works best.
And the tricks for, I don't use them, but isn't the tricks for quickly computing, certainly for fixed estimates, the leave one out error of a GP?
There is, yeah.
You can compute that very efficiently. In fact, you can even try and optimize
I think,
it. But that doesn't work
I don't know if I'm allowed to say this, I think GPML returns it.
I mean, Dave Chappelle did a lot of work on that, didn't he? I think some years ago.
Could be, yeah.
And that's true, yeah, we should have mentioned that, should include that, yeah.
Just a related note, so did anyone had a greedy algorithm for picking kernels or combinations of kernels?
I think James Lloyd.
James Lloyd, maybe, yeah, I think both of them, David and James, and yeah, they're working on that a lot, yeah.
Weren't there two competing posters at ICML about this? One from David Dubenot, one from, I think that they were actually they were even next to each other, and people were
a related thing. I just wondered whether you had a similar perspective as those, where you think they can find.
I think they're doing really interesting stuff, and I like the fact they're doing it. And I think David's doing it using GPy, which is even better. I'm not 100%, but I think that's right.
They even have conditional kernels, so kernels where there's a hyperparameter which switches on complexity in a continuous way. So where you can have parameters which are only there if certain kernels are there, and then you can sort of move. They did this with Frankfurter, moving back and forwards through they had some really fancy name for it as well. It's the parabola kernel or something, which is actually really powerful models for changing the model complexity in a continuous way by changing a hyperparameter.
Other questions or comments, or I mean, in some sense, I think what you've seen is happening. The thing's designed, and I think it works. Is actually as the winter school progresses, we start with the sort of basics of GPs. I don't know, when I was taught French, there was this fad for making us role play and pretend to be in a cafe, but we weren't really in France. So as you learn the language of GPs, what we try to do is make that role playing real and actually start introducing real French cafes and people talking GP languages and talking about open questions.
Is this your way of saying my talk was incomprehensible?
No, I think your talk was very excellent. I think we've seen Philip and Rich's talks really lead us into we've seen open questions, applications where people are using Gaussian processes, but all the answers aren't there. People are asking those questions now. And one of the things we're then designed to do is then go into tomorrow with a real actual workshop which is designed to target those things. That transition is supposed to be smooth. And I really enjoyed hearing Philip and Rich talk today. And I think there's people who are Gaussian process practitioners who've been doing it for a number of years who have been sitting in on these talks, I think, or come for those talks. So it shows that's what you're hearing now is real open questions. I really like that sequential Monte Carlo idea. That's a big problem. If you're doing online streaming data and you want to move your hyperparameters in response to, this is like a big problem on the internet, this is how Google do a lot of things, methods for that, they're open questions, and what Rich presented sounded like a really viable solution for that. So that was an excellent presentation, so I think we just thank Rich again. So we've got the second beer tasting.